So in the other lecture, we were able to create the hypothesis, and we saw that null hypothesis states that the slope, this slope here, or the slope of our estimation, is not different from zero. Here, it doesn't mean that it's equal to zero. We may have some slope, but the slope may not be significantly different from zero. And we give that 95% probability. Normally, we use 95% as default, but sometimes it may be given. If it's not given, then we go with 95%. And the alternative hypothesis states that this slope or the slope is not equal to zero. Or in other words, the slope is significantly different from zero. And that can be proved with the probability value, which will be calculated. And that probability value should be less or equal to the significance level. So if the probability value is greater than 5%, then we know that we will fail to reject the null hypothesis, and therefore we're going to say that the slope is not significantly different from zero. So the next thing we're going to do is to run a regression. And in this case, we will select two variables, and salary will always be our dependent variable, meaning that salary depends on the years of previous experience or years employed, years of education, gender, department, and number supervised. So salary will be our y, which is dependent variable, and any of this will be x, and in that case it is independent variable. So to run regression, we need to run regression, we have to use data analysis. And if you don't have data analysis, you know how to get it by add-ins if you're using Windows. I'm using Mac, and so all I'll do is I'll go to the tools and click on Excel add-ins, and then I'll select the analysis toolpath and click OK. And so when you click on the data, you will see data analysis here. And all I'm going to do is to select a regression in the data analysis tools or toolpath. And this is one of the functions which are in the data analysis. And I'm going to click OK. And so the first thing we're going to do is to input Y range. And so I'm going to select Y range. And then I'm going to select the X range. And so in this case, I'm going to use years of previous experience as dependent variable, independent variable. And so I'm going to select all of this. You can see that I didn't select the whole column, because if I do so, sometimes it can read this section where there's no data, and that will affect the results. And so now, since we have already selected Y, which is the salary, as our dependent variable, and X, which is years of previous experience, as an independent variable, then I will also click on the labels, because the labels are included. And you can see that our confidence level, which we selected already here, is 95%. Normally, as I said, that is default, but it can be determined. And I'm going to select the output range. You can select the new workbook or the new worksheet, but I'm going to select the output range for me to be here, and all I need is the residuals, but you may want to plot the residuals, or you can find the standardized residuals. You can plot normal probability or the line fit plots, but I'm not interested with all this for now, so I'm going to just select the residuals and I'm going to click OK. So when you click OK, then you can see that we have our results here. You can see that we have the summary output. We have regression statistics, where we have multiple R, R squared, adjusted R squared, and standard error, and also the number of observations. And then we have the ANOVA, which gives us the regression, residual, and the total. And in this case, we have the sum of square and the mean of square. And so we have F calculated, and that is our p-value. We call it significance F, which is actually the probability value for the ANOVA, but we are not going to use this for now. So we're going to focus on these results. So we have y-intercept and x. Remember, in our formula, we had y-intercept as a, or we can call it alpha, and then we have the slope, which is b or beta, and so this is actually the beta, and that is alpha. We call them coefficients. And so we have standard error, and the good thing with regression analysis is it gives you the t-value and also the probability value. You don't have to calculate it by yourself. Regression will provide you with this information, and so we are interested with this. That is what we need. Let me highlight it. So our interest is on the p-values, and we need the p-value because if you look at our model here, we need to find this probability value to prove whether the slope is significantly different from 0 or not. So first of all, we will look at the summary, the regression statistics, and we need to see if multiple R is good. Multiple R is correlation, and it is the correlation of the observed value, which is y. Let me show you. It is the correlation between the observed value and the estimation to see if so in this case would like to see if there is any correlation between the estimated value and the observed value. And so you can see that this is not significant. Right here, not significant. As we said before, at least it should be closer, or it should be 0.05 and above, but this one is 0.029 or 0.03. Even if we test it, it's going to be not significant. Now here we have R squared. R squared, in other words, it's known as coefficient of determination, and it shows by how much the estimation explains the actual or the observed value. So you can see that our estimation explains just very little percent of the whole value, or of the observed value. Then here we have adjusted R squared. Adjusted R squared actually adjusts the R squared, and you can see that it's actually negative, and it doesn't explain a significant part of the observed value. So in other words, you can see that there is no correlation. There is no correlation between salary and years of previous experience, because the correlation is very small, not significant. And also, years of previous experience explains this percent of the salary. It doesn't explain any significant part of the salary. And so this by themselves, they prove that we cannot estimate salary by using years of previous experience. And so if you come down here, you will also see the same. Now look at this probability value. We normally don't go with the probability value of the y-intercept, but we are interested with the probability value of this variable, which is independent variable. And you can see that the p-value is 0.85. And remember, we need a probability value which should be less or equal to 5% for us to reject the null hypothesis. And in that case, then we're going to say, we could say that there is a significant, or the slope is significantly different from 0. However, since our p-value is greater than 5%, then the slope which we have found is not significantly different from 0. So which slope we are talking about? The slope we're talking about is this one. You can see there are some values as the slope of the years of previous experience, but this slope is not significantly different from 0. And therefore, we cannot use years of previous experience to estimate the salary. And here we have residual output, meaning that it shows the estimation of each of the salary values that we have. And so if we can go down a little and check this, you can see that the estimations predict the first salary to be 39,428, and so the residual is 26,058, meaning that the first salary is underestimated, and so this is the amount which is left, which we're not able to estimate the first salary. For the second salary also, you can see that we underestimated it, and the difference is this much. Now the third salary is overestimated, and this is the difference. And so you can actually look at those salaries here versus the predicted salary. However, it doesn't make sense at this moment, because already we know that our estimation doesn't work, because the slope of the years of previous experience is not different from 0, and therefore we fail to reject this fact. And so if we fail to reject this fact, then that means that years of previous experience has nothing to do with somebody's salary. Let's try another variable, just one variable, let's say years of education, and see what will happen. And I'm going to squeeze my outcomes here. I'll just put it here for the years of education. Comparing salary as a function of years of education, meaning that if you get more education, do that have, if you get years of education, or in other words, a year of education, will it add any significant amount to your salary if you work in this company? So let's try to do so. And we know that the salary will still be the dependent variable, and the years of education will be our independent variable. And our assumption is salary is a function of the years of education, meaning that a year of education may result in two changes in salary, and that change could be significant, and that's what we are looking for by using this hypothesis. And so we're going to use the same hypothesis to say that the null hypothesis is that the slope of the years of education is not different, or is not significantly different from zero with this probability. And the alternative hypothesis states that the slope of years of education is not equal to zero, meaning that it is significantly different from zero. And we're going to prove by the probability value which will be obtained. So we'll do the same. And so in this case, we're going to click on the data, and then we have to select the data analysis, and we're going to select the regression and click OK. And our Y range will still be the salary, and X range, we are going to select years of education. So I'm going to select the values starting from the label, and therefore I will select the label should be included in the first row. And where do I want my results to be? That will be in another location. So I'm going to select the output range to be here. And I may not even go with the residues for now. Let me remove that and click OK. So you can see that we have our results. And let's start with the multiple R. We can see that the correlation between the observed values of which is our salary, and the estimated values, the correlation is very significant. It is 0.78, which is a really good estimation. Correlation is strong, and we can say that we have strong positive correlation. And if you look at let me write here, we have strong correlation. And so if you look at the R squared, you can see that the years of education can explain about 60% of the salary. So let me write here, years of education explains about 60% of the salary. only 40% is unexplained, but this is a good amount. And adjusted R squared also gives us almost the same, 0.59, which is almost the same as 0.60. We will just consider these two for now, and we can say that our model is okay, that there is a correlation between years of education and the salary, or there is a correlation between the estimated value and the actual value. And also the estimation can explain about 60% of the data. So if we come down here, we will look at, let's start from the ANOVA. You can see that our interest is on the p-value. The p-value shows 2.1752 exponential, or what we call E-1, 10. And so this E, or exponent, shows that this probability is 0.10021752, and it is almost zero. So the p-value is 0.00. That one can be proved by what we have here. In fact, we have exactly the same p-value. And that is the p-value for the slope of years of education. So when you have a year of education, then your salary will change by that amount. And this amount is considered to be significant. It is significant not because of the figures that we have here, but this amount, or this slope, is significant given the probability value. And that proves the hypothesis which we have here, that the slope is not, is significantly different from zero. In other words, this slope is significantly different from zero because this probability value is less or equal to 5%. So that's one observation, very important observation. And so we're going to write the estimated equation. Remember, we have this equation there. So I will paste it here. So in this case, we're going to replace the alpha and beta with, those are the coefficients, so with these values here. So I'm going to write here y estimated equals to, the estimated y equals to, so now for the a, we're going to put 24581.7049 plus, now we're going to put the coefficient of years of education, or the beta, and that is 3009.878 x. This is how we can write the regression equation. So let me increase this a little so that we can see. That's how we can write our regression model. And so you can see that this is this amount is the y-intercept, meaning that salary will be this much regardless the years of education. Or in other words, here, if you put 0 to the x, which is a year of education, then that means this slope times 0 will give us 0. Still, if we don't have any years of education, we don't have this amount, but still the income will be this much. So how do we explain this model now? We'll say that a year of education, 1 year of education, will increase or will contribute to this amount to the salary, or the salary will increase by this much. So we can say y. Let me copy this. So in this case, we can say a year of education. So we'll put 1 in place of x. So the salary will change by this amount when an employee get a year of education. So if the employee goes for get 2 years of education, the salary will increase by this much times 2, or the 2 years of education. So we can actually estimate the salary for this employee. And now, in this case, once you have gone for a year of education, then the overall salary estimated will be the y-intercept plus the slope.